Hello everyone and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about center of mass. Our objectives include identifying by inspection the center of mass of a symmetrical object, locating the center of mass of a system consisting of two such objects, using integration to find the center of mass of a thin rod of non-uniform density, applying the relation between center of mass velocity and linear momentum, and between center of mass acceleration and net external force for a system of particles, and defining center of gravity, and using this concept to express the gravitational potential energy of a rigid object in terms of the position of its center of mass. So let's start by talking about what center of mass is. Real objects are more complex than these theoretical particles we've been dealing with. It's never just an entire amount of mass at some tiny point, and you can treat it that way. Real objects are more irregular, they're more complicated than that. However, what's really nice is from a physics perspective, we can treat the entire object as if its entire mass were concentrated at a single point that we're going to call the object's center of mass, usually abbreviated capital CM or COM, center of mass. Mathematically speaking, center of mass is the weighted average of the location of mass in an object. So how do we find center of mass? Well, with some objects we can do it by inspection. For uniform density objects, the center of mass is going to be the geometric center of that object. For objects with multiple parts, you can find the center of mass of each part and treat it as a point, and then look at that geometric center. For irregular objects, one way you can find it experimentally is to suspend the object from two or more points and drop a plumb line. The lines are always going to intersect at the center of mass, so if you attach it by a couple points, drop a plumb line from it, wherever they cross, right there, that would be your center of mass of the object. Now we can also figure this out by inspection, especially if we have a highly symmetric object. If we have something like this with a uniform density, even though it's a complex object, it's pretty easy to see that the center of mass is going to be, well, right in the geometric center of our object. That one's pretty straightforward. If we have a system of particles, however, we need to get a little bit more detailed. The position vector to the center of mass is the sum of all the little objects, their mass times their position, divided by the total mass of your system. Or if you wanted to look at coordinates, an x center of mass coordinate would be your first mass times its x position, plus your second mass times its x position, and so on, divided by the sum of the masses. And in similar fashion, if you wanted the center of mass for y, that would be m1y1 plus m2y2, and so on, divided by the total mass, or little m plus m2 plus little m3, or total mass, typically written capital M.